Swayam Prabha. Digital India. Educated India.
So, welcome all. So, what we are going to do today, we will learn how to use Mathematica, and for that I will show you the Mathematica interface, and I will also show you how can we do some simple mathematical operations, and then I will solve one problem which is given in assignment 3 or 4 for you, which is Coet flow. For that I will show you how can we simulate that problem. So, what this Mathematica does? This Mathematica is a very powerful tool and it is used for symbolic calculations, mostly for symbolic calculations, but still you can do numerical calculations also. So, I think most of you would have heard about MATLAB. So, MATLAB is a tool which people use for doing calculations, but the limitations with the MATLAB is that it will work very nicely with the numerical calculations, but if you are going to do this symbolic calculation, it will struggle a lot. So, for that we use Mathematica. So, that also Mathematica works very nicely even with the symbolic calculations, and that we will see today in the class. So, what I will do first I will tell you about Mathematica interface. And here I will show you how to do algebraic calculations. And then I will show you how can you do calculus, and in the second part we will solve Coet flow. Which is given in our assignment. So, to start with, I hope that all of you would have solved the assignment already, but I want to write the steps which we use to solve that problem. So, in the Coet flow problem, we have two plates and the upper plate is moving with constant velocity u naught. The distance between the plate has been given as I think d, and the lower plate is stationary. So, this is the a standard Coet flow problem. So, u is 0 here, whereas u is u naught on the top plate, and the flow is happening only because of movement of the top plate. What we have to do in this problem is we have to find what is the startup velocity profile. Right. So, how do we proceed here? I will write only the steps because I hope that you would have done it already, and sir had done it for the Poiseuille flow. So, if you write the equations, governing equation, for the x momentum balance you will get dou u upon dou t equal to nu times dou square u upon dou z square. This is the equation you will get from x momentum balance, and if you will make it dimensionless you will get dou u upon dou t, and I think Reynolds number will be multiplied in this term. This will be equal to dou square u upon dou z square, where here u, t, z all are dimensionless variable. So, let me mark it as a star for now, but in the further I will remove the star and I will use it directly. So, we are trying to solve this equation subject to the boundary conditions which are in the dimensionless form. The boundary conditions will be, I will write it here. The boundary conditions will come as u is equal to 0 at z equal to 0 and u equal to 1 at z equal to 1. The other thing is, this is a partial differential equation. So, you will need a initial condition also, and we will solve for two initial conditions today. I will write those initial conditions here. So, in the first case I will take u is equal to 1 minus cos pi by 2 z, and in the second condition, in the second case I will take u is equal to 0, and this is all at t equal to 0. If not, then I will tell you how we solve it. So, this is a partial differential equation. So, we cannot solve it analytically directly. So, we will have to convert this partial differential equation into ordinary differential equation, and for that we use method of separation of variable. And how do we do that? We will, because here u is a function of t and z, we will say that u is separate functions of z and t, and we will put that value here. Before that, I want to do one other thing, because we are solving for a startup problem. So, sir had first introduced another variable which was deviation velocity, and for that he had obtained the profile. So, I will also proceed in the same way. I will take w as a deviation velocity, and it is nothing but u minus u steady state. So, this u is actual velocity, and u steady state is steady state velocity. And if you will solve at the steady state, this dou u by dou t term will be 0, and you will get directly the steady state profile, and this will come as z. I hope you would have got it. So, this w is nothing but u minus z. So, our differential equation, if we will put value of u from this equation into that equation, it will becomes Re times dou w upon dou t. This is equal to dou square w upon dou z square, and the boundary conditions will remain. Boundary condition now will become homogeneous. So, you will get w equal to 0 at z equal to 0 and w equal to 0 at z equal to 1. So, that is our PD. Now, we put this w as z of z times t of t, and after putting the value of w from this equation to that equation, you will get Re times z, this will come 1 upon Re times z double dash upon z, this is equal to t dash upon t, and this is equal to minus lambda square. And this if we will do this, it will come minus lambda square. So, we need to solve 1 upon Re times z double dash upon z is equal to minus lambda square. So, in fact, this will become z double dash plus lambda square Re times z is equal to 0, and from the another it will become t dash plus lambda square t equal to 0. So, this is our two ODEs which we are trying to solve. Let me write it as equation number 2 and this as 3. I will write this equation as equation number 1. Okay. and the boundary condition for this equation will be z equal to 0 at small z equal to 0 comma 1, and for this equation we need because this is time derivative term. So, here we will need initial condition and we will use that condition from we will use from that first equation. So, we are trying to model these two equations with its boundary condition and initial condition, that is the task for today, and we will do it in Mathematica. So, one way is you can solve this equation directly numerically. The other is you can solve it analytically using method of separation of variable, and the idea is both should give the same solution. So, that is the idea. So, I will do it today. So, other thing is this is this is for t equal to 0. So, if you will put z equal to 0, it will be 1. So, let me put it minus z here. So, this is the initial condition for u. So, that what I wanted, that I wanted u at t equal to 0 and z equal to 0 to be 0. So, I will put z equal to 0. So, then it will be, yeah, I think it is correct only, at z equal to 0 cos 1 will be 0. So, it will be 1 minus 1. So, that will be 0, and at I want it at z equal to 1 to be, at z equal to 1 I want it to be 1. So, at z equal to 23 cos pi by 2 0, so 1, yeah, it is correct. Yeah, this is our problem. So, we are trying to solve these two ODEs along with the boundary condition and initial condition. So, we will do it in a Mathematica. So, I hope all of you have signed in to that link which I had sent in the Moodle, and if you will sign in, you will come to a interface which will look like this. So, any of you felt difficulty in signing there? If not, so we have come to this interface, and you can see that here it is Wolfram cloud. So, this Mathematica was developed by Wolfram, and that is why the name appears as Wolfram Mathematica. If you will come at this interface, you can see here new notebook, new chat notebook, new Wolfram alpha notebook. So, what it does, so I clicked on new notebook. So, it will open a new notebook for me, and it will appear like this. So, now what we do here, this interface is called notebook, and it is really like your notebook. Whatever you write, you can see here. Whatever after writing you will simulate, that will also appear in this folder only. So, the input and output both will appear in your notebook. You can even visualize the output in the same notebook interface. You can see that here we have plus sign, and after that the cursor is blinking, that is called as cell, and each cell we can put our input and we can simulate it. So, what I want to do here is click on the plus sign, and you will get these many options. So, let us click on other styles of text. You will get title, subtitle, chapter, subchapter. So, it is same like you write it in your notebook, you make a title, you make subtitle and all. So, like that, let us click on title, and in the title I want to write introduction to Mathematica. Right. So, if at any point you feel difficulty or if you are not able to do the same thing, you can ask us. I will stop and I will tell you. So, that was for title. Now, here I can write anything. I want to tell you a few things before simulating any code, that I will write all those things here. Let me write it as subsection, and you can do it without clicking on plus sign also. So, if you are in Windows, you can click Alt 5, so you will go to section, or alt 6 you will go to the subsection. So, like that also you can go directly. So, in Mathematica, yeah, so suppose I am here this how I wrote this introduction to Mathematica. It is not coming. Where are you? At the interface. Others have gotten it. So, in Mathematica, if you will click on plus sign, you will have other styles of text, and you click on that other styles of text, you will get that title, subtitle, chapter. So, you click on any of this. If you want title, you click on title. If you want subtitle, you click on subtitle. Okay. So, let me tell you now other thing. So, this Mathematica has one knowledge data center. A lot of data is collected there. Even the AI tools, they have collaborated with this Wolfram knowledge center, and they take the data from there. So, you can understand the how powerful this Mathematica is. It has very big collection of data. So, I can directly ask Mathematica that give me something, and how can we do that? We click on, so come to the cell where you have plus sign and one cursor blinking there. There you click equal to sign. So, an orange color equal to will appear, right, and you can ask here anything like derivative of sin 4x. So, I am asking like regular text. So, this is called as, and click on shift enter if you are in Windows. If you are in Mac, you click shift return. So, if you will click it, it will give you 4 cos 4x. So, click come to any cell, and then you click equal to sign, equal to in from your keyboard. What? Yeah, I am also getting orange color only. So, that is the way, and you can ask anything. You can ask even population of India, and it will give you number of people living in India. Okay. You can also ask like 3D structure of caffeine. So, it gave me the structure of caffeine. Even I wrote caffeine as a wrong spelling, still it gave me the structure of caffeine. So, that is how strong or powerful Mathematica is. So, these are about you can even rotate it, you can see the 3D structure of caffeine. So, now let us come about mathematical calculations. So, I want to tell you 3-4 things before starting mathematical calculations. The first one is, in Mathematica we write any command or function with the capital letter. So, press alt 6, you will come to a subsection, and here you can write any command or function is written with the capital letter. Or function starts with the capital letter. What does it mean is, like if I have to write sin x, I will start with capital S. If I have to write cos, I will again start with capital C. So, these are functions which I need to put start with a capital letter in Mathematica, whereas if you are used to using MATLAB, they are all letters start with a small. You have to write tan, then I will write with a capital T. You have to write log, I will write with the capital L. The other is to give, so this is about function. The similar thing applies with the commands, like some commands are simplify, expand, sum, series. These are all some commands which do certain type of operations in Mathematica. These all commands will also start with the capital letter. So, the other point is to give any argument to a function or to a command, you should give it in a square bracket. What does it mean is, like we have sin, so I want, if I want to put sin x, I will write a square bracket and then I will put x. So, that is how we put function, argument to a function. So, cos is another function, if I want to put inside it, I will write curly square bracket and then x. Similarly, if I have to simplify an expression, I will put simplify and I will start with a curly bracket and then I will put expression here. And the similar thing applies with expand, sum, series and all other Mathematica commands. Okay. The third thing is to evaluate any command, you need to press shift and enter key at the same time. So, we will see it now only, that how we get it. So, if everything is clear till this point, can I do some mathematical operation? If you are feeling difficulty anything till now, even in understanding, you can ask us. Okay. So, let me ask Mathematica to do some simple operations first. I will ask Mathematica to add 23 plus 45. So, you write 23, then plus sign, then 45 and press shift and enter. If you are on Mac, you put shift and return. So, you can see here that we have here, I got the output as 68. So, here we have, here it is showing in 5, that is input number 5 I have given as 23 plus 45 and I am getting output as 68. So, that was a very simple calculation for Mathematica to do. Let me ask it to do 1 by 3 plus 7. That is again very simple calculation, and you can see here that Mathematica has returned a value which is a fraction, whereas if you will do in MATLAB or some other software, you will get it to be in decimal. In Mathematica, it is giving me the exact number, that it is 22 by 3. So, Mathematica works with infinite precision. It will return you the exact value rather than giving some precise value. So, it has not returned to it to some number with some decimals. It has given me 22 by 7, which is exact. And if I want to get the numerics of that what is the numerical value, exact numerical value for this, I will put forward 2 forward slash and I will put capital N. So, this will give us the numerical value for the given input. and you can see that it has given me 7.333. So, Mathematica commands are very easy to remember, because they are general English commands like simplify, expand, for numerics, n, for integrate, integrate and all. So, the point here is that Mathematica works with infinite precision, and it will not give you the decimal form output until you ask you to do it. Yeah, so this is about plus. Similar thing you can do for minus. You can put in the earlier command only. Let me subtract 6 from here and press shift enter. So, it will give me again the how I wanted to show you how addition and subtraction is done. For multiplication, you can do again the similar thing. You can write either 2 into 3, or you can write 2 and a space. If as you will give a space, the Mathematica will consider it to be into. So, you do not even need to write into if you do not want. So, even if you write 2 a space 3, that will also work as the same, and if you will press shift enter, it will give you the same result. Here you do not need to put any space. Here this was the original output. I put double forward slash and then I gave shift n, and then I press shift enter. So, capital N you need to put. So, I said all the commands in Mathematica should start with capital letter. So, that is why you should give capital N and then press shift enter. So, you will get the output. Okay. You did not get Shivam? N is giving the numeric value. So, if you will run it without n, it will give you 4 by 3. So, it is the exact number, but suppose I want the numerics value of that, I will no, I think you would not have executed it rightly. You press double forward slash and then capital N. It cannot happen. Or you can try in another way, you put capital N in the front of that input and then a square bracket, and then you close the square bracket, and then you press shift enter. That will also work in the same way. Okay. For division it is very simple, 2 upon 3, it will give you the value. Again, if you want the numerics value, you press double forward slash n. Okay. Yeah, so we have seen the simple arithmetic operations. Now we will do some differentiation and integration, that how can we do that. So, for differentiation, one simple command is capital D. So, this is like if you want to differentiate sine. So, again I started sine with capital S, and I have to write, let us say, sine 4x. So, I started again with a square bracket and I will put 2 space x. So, it will give me sine 2x, and then I will put comma and x. So, D is for differentiation, then you put the expression which you want to differentiate, and then separated by comma you put the variable with respect to which you want to differentiate. So, this will give us differentiation of sine 2x with respect to x, and this is cos 2x. The other thing is, after every output, Mathematica is showing some suggestion that do you want to plot, do you want to take x derivative, do you want to integrate it. So, you can directly, if you want to plot 2 cos 2x, you can directly click on plot. So, it will give you the plot of cos 2 cos 2x. Okay. I hope you are following till this point. Now, let us understand how can we do integration. So, suppose for integration the command is integrate, and here if you will come to integrate, it is showing us here integrate. I clicked on that integrate, and then here it is showing down arrow, I clicked on that. So, you can see here we have many options for integrate. The first one is for indefinite integral, where there is no limit for x. The second is for definite integral, in which we can put even the limits for x. So, let us do for definite integral, and again I want to, let us say that I want to integrate cos x into, I will put a space and then sin x, and I want to integrate it with respect to x. So, I am putting x, and x limit let us say minus 3, y limit let us put as 5, and if I press enter, shift enter, I got the answer. So, you are just putting the integrand and then limits and pressing shift enter. Again you can see that Mathematica has given us output which is in the form of cos 2, cos 6 and all. It has not converted it into decimal form. This is again because it is giving us exact value of any output, and if you want the numerics value, you can put /n, and it will give you the numerical value of that. And again here you can see show all digits have suggested by Mathematica. If I will put that, it will give us all the digits. So, this is about differentiation and integration. For differentiation you need to put d, a square bracket, the expression, and then the variable with respect to which you want to differentiate. The other thing is we can also differentiate twice, like if you have to differentiate any function 2 times, what I will do, I will go to the earlier command only. So, we have sin 2x. If I want to differentiate this function 2 times with respect to x, I will put a curly bracket before x, and I will put x comma 2, and then I will close the curly bracket, and if you will press shift enter, it will give you the differentiation of sin 2x twice with respect to x. Okay. Similarly, for the integration also you can do, you need to put one more integration sign before the earlier expression, and then you will get twice integration of that. So, because we have d square z upon dz square in one ODE, so that is why I showed you that we can write it directly by putting x in curly bracket and separated by comma 2. We will see it later also. The other thing is in Mathematica we have 3 equal to. So, we have 3 equal to's as equal to, let me put again alt 6. So, I will come to a subsection. So, we have one equal to as simple equal to, other equal to we have is other equal to which we have is semicolon, colon equal to, and the third is double equal to. So, these are the 3 equal to which we will use in Mathematica. So, let us understand what this 3 equal to means. So, if you have to assign value to any variable, you will use single equal to. Suppose I have to say that x is equal to 5. So, then I will use single equal to, and I will press shift enter. So, now, so what it will do? It will assign value of x as 5. So, in latter section, latter cell, if I will use x and press shift enter, it will give me the value of x as 5. Whereas, the second one, which is colon equal to, that is used to create function. So, suppose I have to create a function which is f. Why I am writing with a small f? Because the Mathematica have inbuilt all the functions with capital letters. So, I am writing with a small letter, so that if someone is reading my notebook, he can understand that it is the function which has been made by the user, not by the Mathematica. So, I am writing a small f, then a square bracket, and let us say that we want to make function of y. So, I am writing f y and then underscore, then you close this bracket, then you write colon and then equal to, and any function you want, suppose y square plus 5 y plus 8. So, this colon suppresses the output. So, suppose I run this command with colon, I will not get any output, because this colon suppresses that, whereas if we will run without the colon, I will get it to be y square plus 5y plus 8. So, this colon will suppress your output. So, this is how we make function in Mathematica. Suppose you have to find the value of f of 5, then you will put f a square bracket 5, a square bracket closed, and press shift enter, you will get the value of f of 5. So, this is how easy Mathematica is used. The third is equal to sign, that we use for showing any equation, like we have equations z square plus lambda square z equal to 0, t dash plus t equal to 0. So, to show those equations we use double sign, double equal to sign. I can show you with a simple example. In Mathematica there is one command called solve. So, what solve does? It will solve the algebraic equations. So, suppose I want to solve this equation only. So, I copied and pasted it inside the solve, and if I want to solve for y, so then I will put it inside a solve command and I will put the expression, then I will separate it by a comma. So, what it does, the expression which you want to solve you put first, and then if you want to find the roots of that expression you put it like that. If I will run it like this, it will give me an error, and you can see it that it is not a system of equation. So, to make it system of equation I will put double equal to 0, and if I will run with double to equal to 0, it will give me the value of y, the roots of that equation. And again you can see that it has given me in terms of fraction, so it is exact root. So, this solve is finding exact root analytically, like we do b minus b plus minus root under b square minus 4ac upon 2a, like that it is solving and giving us the output. You can use this solve command even for very big expression and it will work very efficiently. A similar kind of command for solving algebraic equation is n solve. So, you just put n. So, it is like it will solve the same equation numerically, and if you will press shift enter, it will give you the numerical value. So, you can see that in this case you are getting the things in the decimal form, whereas in the earlier case it was in fraction. So, solve command solves any algebraic equation analytically, whereas this n solve command solve any equations numerically, where it takes some initial guess and it solves. A very similar command, so solve and n solve is used to solve algebraic equation, but we have differential equations, right. So, to solve differential equations we use d solve, and d solve is just you had solve earlier because it is differential equation, so put d in front of it. So, d solve will solve differential equations. So, let me show you one thing here, that if you will come here and oh god, yeah, if you will come here, here in the search is there, right. In the search you can put d solve. So, you will search here d solve, it will give you some suggestions, like these are the ways in which d solve can be used. So, you can use d solve to solve a differential equation without any variable or without any boundary conditions, you can use with dependent variable and independent variable. So, D solved here equation is the equation which you want to solve, u is dependent variable which you want to solve for, and x is independent variable. Like in our case, it is z double dash plus lambda square r e times z is equal to 0. So, that is your equation. Z is your capital Z is your dependent variable and a small z is your independent variable. In equation number I think it is 2. So, there z double dash plus lambda square r e times z equal to 0, that is your equation, and that capital Z is your dependent variable and a small z is your independent variable. So, let us try to solve one problem with D solve, and what I will do, I will use the same equation, which same differential equation which we have got for coed flow. So, I am writing D solve and then the equation for differential equation, which is z double dash of z. So, if I am putting double dash there, it will and here z is there. So, it will automatically understand that it is differentiation with respect to z, or you can do it in another way also. You can put z of z comma z comma 2. So, this is how I think I have told you to differentiate. Yeah. Is it fine now? Fine. So, here this command is nothing but z double dash. Okay. So, here we have capital Z which is function of a small z, and I am differentiating it with twice with respect to z, that is why capital D square bracket, and here in the curly bracket we have z comma 2. And what is after that? Let me see it, plus lambda square. So, I will write lambda square and then I will give a space 4 into then Reynolds number times z of z. Okay. This is equal to 0, and let me do in this much of magnification. So, this is equal to 0 and the boundary conditions are z at z equal to 0 is equal to 0 comma capital Z at z equal to 1 is equal to 0, and so these are the equations. I will show you. So, these are the equations which we have z double dash plus lambda square r e times z equal to 0, and these are the boundary conditions which we had to solve this differential equation. And then I will write the dependent variable. So, we have dependent variable as z of z and the independent variable is a small z. Okay. So, we need to write all the equations inside a curly bracket. So, I started curly bracket here and I close it, and if you will press shift enter, it will give you the value of z. You just need to put the differential equation boundary conditions into the dsolve command, it will give you the solution. One of the important thing which I want to discuss here is, you can see two solutions for z. One is 0, which you can see the second option, other one is C1 sin lambda square r e times z, where it is showing that n is greater than equal to 1 and lambda square r e is equal to n square pi square. So, dsolve solver uses solves differential equations analytically, that is why it is giving you solution in this form. you can see that the equations, differential equation and boundary conditions are homogeneous, right. If you put z equal to 0 in differential equation and boundary condition, you will get that it always satisfies. So, means the differential equation and boundary conditions are homogeneous. So, 0 is always solution for this, and that is why Mathematica is saying me that 0 is always solution, whereas Mathematica is so powerful that it is also saying us that there is another solution which is also in the form of sine function. If you will solve it numerically, you go to the MATLAB and solve the same equation with the same boundary condition, you will get 0 as the solution. Even in Mathematica also, if I use the ND solver and if I solve it, it will say that it has non-numerical value, because when it will solve numerically, the algorithm will take the shortest path and it will say you that the 0 is always a solution, whereas analytically you can see that it has another solution also which is in the form of sine function, and you can verify it by doing calculation with your hand also. And the another thing is this lambda square Re is n square pi square. So, what I will do, I will write that z of z is equal to, it is C1. So, I will write C1 times this sine function, and I am replacing lambda square Re with n square pi square. So, root over n square pi square will be n pi, right. So, it will be n times pi is written as capital Pi times a small z. So, this is our z of z. So, what I did, we had two differential equations. The first one is homogeneous differential equation. I put that differential equation along with its boundary condition in desolve command, and it gave us one solution which gave us two solution. One is 0 as solution, other is non-zero solution. So, we always want a non-zero solution, so that is why we have chosen the non-zero solution for further calculation. Okay. So, we got z of z. Now, we need to find t of t, which we will get from the second equation, third equation, equation number 3. So, let us do the calculation in the similar way. We will write desolve, and we will write, I will write here d of t comma t, this is equal to this plus lambda square times t of t, this is equal to 0, and we do not have the initial condition here for t, because the initial condition is there in terms of w, we do not have the initial condition for t. So, that is why we will put it as t of t only, we will not put the initial condition, and we will solve it. You will solve it, you will get the solution as C1 e to power minus lambda square t. Okay. So, what I will do, I will combine these two solutions, because w is nothing but z of z times t of t. So, I will multiply both these two solutions, and I will write w of x of w of t of z t comma z, that is equal to z of z into, I am combining this C1 and this C1, and that will be e to power minus lambda square t. So, E in Mathematica is written as e to the capital E, and this is minus lambda square is nothing but n square pi square upon Re. So, I will write it as n square pi square upon Re, and one minus sign also here. So, what I am doing, I am replacing the value of lambda square with from here, which is lambda square is nothing but n square pi square upon Re, and this is the value of w of t of z, which is deviation variable, deviation velocity value. right. Now we need to calculate this C1 because that is unknown to us, that is only unknown to us which we have to find, and that we will find using the initial condition because that is yet to be satisfied. We have satisfied the two boundary conditions, but we have not yet satisfied the initial condition. So, if you remember, I forgot to write it there. So, if you remember the value of C1 is, I can show you there again. Yeah, so again one more thing which I want to clear it here is this W is deviation variable, and if you take the initial value for W, that will be u minus u steady state, right. So, that will be 1 minus cos pi by 2 z minus z, right. The initial condition for W will be 1 minus cos pi by 2 z minus z, because you need to put it there, because W is u minus u steady state. So, we will calculate this C as, I will write the exact expression in form of integration there also, but you believe me that it will be integrate, it will be 1 minus cos pi by 2 times z minus z, and this is multiplied by sin n times pi times z, and this should be integrated from z equal to 0 to 1. This is divided by integrate it integrate sin n pi z square from z equal to 0 to 1. So, this is the value of C1, and I can put here W of t of z, and it will W of t comma z, it will give us the value of W. So, this is your W now, which is deviation velocity value. For this integration, I can tell you just after the class. So, what you need to do, this is deviation velocity profile, you need to add it with USS, because u actual velocity profile will be W plus USS. So, this is W, so actual will be actual velocity will be equal to W of t comma z plus USS, which is nothing but z. So, this is your actual velocity profile. Okay. So, we got the actual velocity profile, we can plot it also. So, you can see that this actual velocity profile is a function of t as well as, I think t is missing here. So, t should be here, I will run it again. So, this actual velocity profile is function of t and z both, and the again question is what will be the value of n, because from the solution we had gotten that n is greater than equal to 1. So, n can be 1, 2, 3, 4, 5 anything. So, what you need to do, you need to take multiple values of n, and this is nothing but like summed over n. So, if you will take value of n, then it will be solution will be e to power minus pi square r e, and the value of wherever n is there it will be 1, whereas if you will take value of n equal to 2, it will be the value of this w z t at n equal to 1 plus the value of this wzt at n equal to 2. So, that you can get using some command. So, I do not have time here, so I can show you. I have written the code earlier with the Mathematica only, and I have done a lot of things here, but you can see that I hope this is visual to you. So, W is u minus u steady state. So, u will be W plus u steady state and u steady state is z. So, I added that, and I took two values of Re. In the first case I took R equal to 0.01 because that is a parameter for us, I can choose any value, and then I plotted u. We have the expression for u same, u equal to z plus actual velocity, and we plotted it with respect to time and z, and you can see that this is the velocity profile which will look in 3D. Whereas, if I fix any time, and so suppose here u is function of t and z both, so it was here, and suppose I fix any time, suppose I want at t equal to 10 power minus 5, 10 power minus 4, and I want to see how u varies in z. So, that you can do here. So, this forward slash that dot, that is command for replace. So, in u, because u is function of t and z, wherever t is there I will replace with that t equal to 0 with this command. Similarly, in the second case I will replace it that replace the t with 10 power minus 4, and similarly I have taken 3-4 values of t and I plotted how u varies in z, and you can see that this is the velocity profile which looks like. The other thing is which you can see is that as time has reached t equal to 1, this black is the velocity profile, and you can see that this is nothing but a profile for u equal to z, means at t equal to 1 the system has reached the steady state and the profile velocity has value u equal to z, which you can see from here, this graph. I have also solved it using direct numerical simulation. So, this approach was using analytical solution. We considered method of separation of variable and then we solved the differential equation. The similar thing you can do without by direct solving it numerically, and for that you can ND solve is another command in Mathematica. So, what I did, I solved the same equation using ND solve, and you can see that this is the velocity profile. I will run everything at a time and I will show you both the profiles which I got using analytical solution and numerical solution. So, the first one, this profile, this is analytically obtained profile, a numerically obtained profile, and the second one is analytically obtained profile, and you can see that both matches. So, you can use like no matter in by which way you are solving, you will get the similar velocity profile, and it shows that even with the analytical solution, like it shows the verification of your result, that if you have got something using numerical solution, you can verify that using analytical solution. So, this is all about Mathematica. If you feel any difficulty, you can ask any one of us. We all use Mathematica and MATLAB. So, let us talk about that integration which we did. So, we have W as u minus u steady state. So, W at t equal to 0 will be u at t equal to 0 minus u steady state at t equal to 0, and from here, because this W at t equal to 0, u at t equal to 0 is 1 minus cos pi by 2 z, and this is nothing but z no matter what is the time, and so this is initial condition for W at t equal to 0. And if you will see our expression for W, it was W was equal to some constant C1 into e to the power minus n square pi square upon I think Re, times t times sin n pi z. So, what we do? We put t equal to 0. So, as t will be equal to 0, this term will be equal to 1. So, it will be equal to 1 minus cos pi by 2 z minus z. This is equal to C 1 times sin n pi z. And you can recall the concept which you have learnt in your mathematics course, that when we have to find C 1 from this type of equation, because sin n pi z is orthogonal function, we can use that property and we can integrate both side with respect to sin pi, integrate both side by multiplying sin n pi z, and that is why you will integrate it 1 minus cos pi by 2 z minus z. You will multiply sin n pi z both side and you will integrate it with respect to z from z equal to 0 to 1, and here this side will be C 1 0 to 1 sin square n pi z t z. So, C 1 will be nothing but this integration divided by this integration, and that is what I had done in the Mathematica also. So, from there I will get C 1, I will substitute the value of C 1 here and I will get W. So, this is what you have learnt in your Mathematica course, in your mathematics course.